Slava Shokurov. This is the first time I give an online talk, so it may not be perfect. Usually I don't use this system, so hopefully everything will go according to plan. Okay, everyone can see my slide now?
Mm-hmm. Yes, it works.
Okay, great. The plan is that I will talk about some works of Slava Shokurov. Of course, I'm not going into everything that he has done, but only a sample of what he has done. And mostly that will be in birational geometry. And so I will ignore pretty much everything else he has done. But first, let me start with a short biography. Slava Shokurov was born on 18 of May 1950 in Moscow, Russia. So today is really his, so we are celebrating his birthday. He grew up in Moscow, and then he attended Moscow High School #2, which is a famous school in Moscow. And I think other famous mathematicians also came from this school. Now in this school, university professors also used to come to this school and give seminars. And Shokurov attended one of the seminars by Iskovsky, his a close friend, and I think probably that's where the whole thing started, in the sense that he got interested in algebraic geometry and also later on got interested in birational geometry. So in a way, probably Iskovsky is the starting point of Shokurov maybe mathematical career. And now after high school, he then entered the undergraduate at the Faculty of Mechanics and Mathematics at the University at Moscow State University. That's from 1967 to 1972. So you'll see a lot of dates here. I hope that I have got the dates right. And I should thank Vyacheslav for providing some of the information and also some of the photos here. Then he did his PhD degree also at Moscow State University under Yuri Manin from 1972 to 1975. And then he got his first job, which was at the Institute of Technical and Scientific Information from 1975 to 1982. After that, he got a position at the Vyacheslav State Pedagogical University, and he was there from 82 to 90. And then he spent 1 year at the Institute for Advanced Studies in Princeton. That was in 90 to 91. That's when also many Russian mathematicians left Russia, either because of the issues with the collapse of the Soviet Union. And then after that 1 year at Princeton, he moved to Johns Hopkins University, where he has been a professor ever since. So that's almost like 30 years. But he is also a non-tenure member at the Steklov Mathematical Institute in Moscow, and he usually spends the summer and maybe the winter breaks at this institute. Shokurov trained at least 9 PhD students, although I think he trained maybe more students jointly with other people. But I know about these 9 people that include Abe, Ambro, myself, Cheltsov, Yifei Chen, Choi, Katron, Marshburn, and Jihun Park. And interestingly, most of these people, their surnames start with A, B, or C for some strange reason. you can see 4 of the students in this photo here. This photo was taken at, I think, at Pohang in South Korea a few years ago in a workshop devoted to the Shokurov family. So he has, of course, a much bigger academic family, and you can see some of these people in this next slide. So this is a really very beautiful poster. It was drawn by Vyacheslav wife, specifically designed for this conference, which was called the Shokurov, and it was held in December 2017 in Pohang, Korea. So every time I look at this, I can't stop laughing for like 5 minutes. Okay, that's a very short, maybe a few more words. And then Shokurov, initially he worked on parts of algebraic geometry, you would say a bit close to arithmetic geometry. For example, even during undergraduate, he did some research on the Noether-Enrico-Petri theorem. And then he worked afterwards on modular symbols and then cast forms, Kuga varieties, and so on. But it didn't take long before he entered the field of higher dimensional algebraic geometry or birational geometry. And I guess, I'm not sure if I'm completely correct, but I think this was also the influence of Iskovsky, who was his close friend, and then he was doing birational geometry, so Shokurov entered this field. And also, I remember a long time ago, Shokurov, Slava told me that, in fact, one of the reasons he entered this field was because he thought that not many people work in this field, so it's a good place to work, not overcrowded. But soon afterward, actually, it didn't take so long before this field grew and a lot of people started working in this field. So I'm going to ignore his other work, but just focus on the birational geometry side. He has played a really fundamental role in shaping this field with his amazing theorems and also conjectures and just definitions and his deep insight. So it's really an amazing and colorful mathematical career, but he, as a person also, he's a really very kind and a very generous person. In fact, I would say that he's one of the kindest person that I have ever met. He basically avoid, I think, on a personal level, all kind of politics, especially politics in the mathematical community, which in a sense may be a bit rare for people working in the academic world. So today, let's then celebrate his birthday together also with his amazing mathematical achievements. I think this photo was taken maybe at the workshop in Pohang in Korea a few years ago. So by the way, if anyone send me a chat, I actually can't see it on the screen. So I think maybe you better speak up. Okay, so that was a short, very short biography. Let's now talk about his mathematical work. First, I will start with giving an overview, an introduction into birational geometry for people who are not familiar, although many here are experts already. I will also work only over the complex numbers, although you can also work over any algebraically closed field of characteristic 0. Many things will make sense also in positive characteristic, but I will just ignore that for today. Now, variety in this talk will just mean a quasi-projective algebraic variety defined over the complex numbers. We say that two varieties are birational if they have isomorphic open subsets. So in other words, if they are biomorphic in the sense of geometry. And then birational geometry basically aims to classify varieties up to birational equivalence, birational isomorphism. This is quite natural in a sense because, for example, varieties in general can be very complicated, very singular. Then a very natural first step is to resolve singularities of an algebraic variety, and that is a birational transformation. So it's quite natural then to work with birational classes rather than just a fixed algebraic variety. So in fact, in a lot of deep and important theorems in algebraic geometry, they are stated for mostly, in many cases, for smooth varieties. So in a way, it's a quite a natural and reasonable way to work up to birational isomorphism. And then what we want to do here is that in each birational class, find some nice elements, some manageable representative in each birational class, maybe not one, it could be many of them, such that we can classify these as special, these nice elements. For example, that could mean we want to construct their moduli spaces. Now, this process involves a lot of birational geometry in the sense of doing birational transformations, but in fact, it also involves a great deal of biregular geometry. In fact, many of the statements we prove are not really birational. They are biregular, but the techniques are usually birational in the sense that if we have one fixed variety, we want to prove something about them, we, for example, take a resolution or change the model to get some more information, and then we come back to the original variety and we prove that the statement. So in that sense, we are just doing biregular geometry, not birational geometry. So for example, base point 3 theorem that I will discuss later is just a biregular statement, or abundance theorem or conjecture is a biregular statement. It's not really a birational statement. Now, the canonical divisor, which I will denote by K, is central to this story. So it will appear almost everywhere. Okay, let's start with the most simple case, that's of dimension 1, which was already done in the 19th century. Now, in this case, luckily, every birational class contains a unique smooth projective curve, a unique model. So finding that nice model is almost in a way automatic. There isn't much to do there. If you take any arbitrary curve in the class and just take the normalization, it will give you this smooth, unique smooth model. So that step, that part is quite simple. And then the next step is to classify these smooth projective models. And that's done first by defining the genus of the curve, which can be defined in many different ways. It can be defined as global section of the canonical bundle, or as H1 of the structure sheaf, or topologically as the number of holes in X, where we consider X as a Riemann, a compact Riemann surface. And if the curve is embedded in, for example, in P2 in the projective plane, we can also define this by just looking at the degree of the curve. Now there is a rough classification here according to the genus. If the genus is 0, that exactly means that the degree of the canonical bundle is negative, in which case there is only one possibility, which is just K, which is X is the projective line. But on the other hand, if genus is 1, then the degree of the canonical bundle will be trivial, and then X will be an elliptic curve. But if genus is higher, then degree of K is positive, and that means X is of general type, which simply means that there are too many of them. So just group all of them into one set, and that will be general type. However, they share a lot of properties, although there is a huge number of them for genus higher than 1. And then what we do here is that we individually study each of these smooth projective curves. For example, we can investigate the linear system given by the canonical divisor or by other divisors. And then the next step is to study these varieties, to classify them in the sense of a moduli. So we try to construct a moduli space for curves of fixed genus G. This picture here is just a topological shape of these curves. So they started actually in the ancient times, already in the Babylonian times, but it's still ongoing, very active research. So that just shows how complicated and how interesting algebraic geometry is. But when we go to higher dimension, then everything becomes even more complicated. So for example, in dimension 2, we can again start in each birational class, we can find a smooth model. So let's just start with a smooth projective surface, let's say X. And now the thing is that the canonical bundle may not be uniformly negative, trivial, or positive on the whole space. That basically means that the curvature may not be uniformly negative, positive, or trivial on the whole space. And then we try to somehow make it uniform if we can. And this leads to the so-called minimum model program, which is just a sequence of birational transformations where in each step we get rid of some curve where k is negative. So in other words, we try to make k as positive as possible, unless it's already just completely negative. So after finitely many steps, this process will give us some y such that it satisfies one of these properties. Either k is negative along some fibration. So in that case, we will get something like a P1 bundle, at least generically, or we get ky being trivial along some fibration. And that usually means we get an elliptic fibration. Or if this doesn't happen, then ky becomes positive everywhere. So we will get rid of all the negativities. And even in this case, we can get rid of all the trivialities where k is the canonical bundle intersects some curves trivially, then we can even get rid of those and get something that is completely positive, or more precisely, k become ample. So this process will either give a negative fibration or trivial fibration, or we can just make k totally positive. Now, as I said, this is the so-called minimal model program, which goes back to more than 100 years ago for surfaces. And so people try to mimic this program in higher dimension, but it took actually a very long time, at least maybe something like 70 years until people realized what they should do in higher dimension. Although there were lots of work, for example, by Fano, by Severi and other people on specific cases, for example, on Fano varieties, special examples where they try to do this birational classification, but the general framework took a very long time to be realized, and that was only in the 70s, of course, after great works of people like Zariski and also Hironaka and so on. Now, so what we will do in higher dimension. So suppose that we start with a projective variety. We can start maybe with something smooth, but it turns out that that's actually not enough. We have to introduce singularities in a systematic way, but for most of the talk, actually, I will not really say much about singularities, although I mention it a lot. So suppose that X is smooth, or it has some kind of nice singularities. Then we can define three very special classes. These are the Fanos, Calabi-Yaus, and canonically polarized. They are simply...
Sure.
Yes.
May I ask you a stupid question?
Yes, sure.
If your X was P2, then in which category is it on the previous slide?
P2, let me go back. So if it's P2, it's actually is in the first category because k is negative everywhere. So the z in that case will be just a point. X will be just equal to y and z will be a point. So you get a vibration to just a point.
Okay.
Okay, so let me define these classes in order to describe the program in higher dimension. Given a variety x, we say it is Fano if the canonical bundle is totally negative. It is anti-ample, which is exactly the simplest cases are the projective spaces. We say this is Calabi-Yau if k is numerically trivial, for example, abelian varieties or K3 surfaces. And we say this is canonically polarized if k is totally positive. It is ample. For example, you take a hypersurface in Pn of high degree, you always get a canonically polarized variety. In fact, the next example will just be about hypersurfaces. So for example, suppose that x in Pn is a hypersurface of degree, let's say r, then we have three possible cases according to the degree. If the degree is less than n+1, then we get x affano. So for example, in P2, any curve of degree 1 or 2, so let's say assuming that is smooth, will give you affano, which in that case is just a P1, just a rational curve. But if the degree is precisely n+1, then we get a Calabi-Yau. Again, in the plane in P2, degree 3 gives elliptic curves, which are Calabi-Yaus. And finally, if the degree is more than n+1, then we get x canonically polarized. So we can see these things just from the definition and just applying adjunction formula. Another basic example is the case of curves, which I mentioned before. For smooth projective curves, the genus will tell you exactly what classes we have. Genus 0 is precisely Fano, just P1. Genus 1 is Calabi-Yau, which just means elliptic curve. And genus more than or equal to 2 is canonically polarized, which is the same as general type. So at least if you are not a birational geometry, you can keep these examples in mind for the rest of the talk maybe. Okay, now knowing these three special classes, then I can talk about the birational classification a bit more precisely. Now the big step, the huge step in the birational classification, it's summarizing the next conjecture, which is actually a mixture of several conjectures. It says that if you start with any smooth projective variety, x will, in fact, if you start with an arbitrary variety, it doesn't have to be even smooth because you can take resolutions, then there is a projective variety y birationally equivalent to x and maybe singular, but with good singularities such that either y admits a Fano vibration or y admits a Calabi-Yau vibration, or y is canonically polarized. So there are only three cases, and that's in a sense is really amazing that there are not like 20 cases, but only 3 cases. There is a good reason for that. The reason is because we just have positive 0 or negative real numbers, and birational geometry, in a sense, this classification is basically telling that you can go from numerical properties to geometric properties. So just this numerical, for example, k intersecting every curve 0 will give you something geometric. So that's, in a way, usually the challenge is to go from numerical properties to geometric properties. And so that's why we have only 3 cases here. And this conjecture is known in some cases. For example, in dimension 2, this already goes back to more than 100 years ago. It was worked out by the Italian algebraic geometry school, especially Castelnuovo and Birkar, but there were also other works later by Zariski, Kodara, Šafarevich, and so on, who clarified this picture and also generalized it to more cases. For example, Shafarievich worked this out for arithmetic surfaces over the spec of Z, for example. And then dimension 3, it took a very long time. It was worked out only in the 70s up to the early 90s by work of a large number of people, but especially Kawamata, Kolar, Miyaoka, Mori, Reed, and Shokurov. These are like the big player, but also before that there were works of Fano, Hironaka, who proves resolution of singularities, Itaka, whose philosophy of open varieties, in a way, it evolved into the theory of pairs, and then, of course, Iskovsky, classification of Fanos, and so on, and Manin also played a role. And this all happened in the 70s until early 90s. But in higher dimensions, it took some time until there were progress in dimension 4 and higher. At least for the case of X general type, the conjecture was proved finally by myself, Kashini, Heiken, and McKernan after, of course, after work of Shokurov. But otherwise, the conjecture is still quite wide open. Now, the big question is, if you are given X, how to get Y from X? Now, if you start with something of general type, so general type more precisely here means that the canonical bundle is big, or you can say the Kodara dimension equals to the dimension of the variety, which roughly speaking simply means that when you look at the multiples of the canonical bundle, you get a lot of sections. Its sections will grow at the rate of m to the dimension. If we have that, then we can in fact go from X to Y, just jump from X to Y directly by setting Y to be the product of this algebra over the complex numbers. But this, in a way, this makes sense only if we already know that this algebra is finitely generated. Otherwise, this will be quite useless. Now, in practice, the thing is that to prove that this algebra is finitely generated, we actually do a lot of minimal model program, the process that I mentioned, in order to arrive at this finite generation. Although there is now more direct proof of finite generation, but in practice, it's really the program itself, the step-by-step program going from X to Y, which is interesting, than just going directly from X to Y. So what we really like is a generalization of the minimal model program for surfaces. And in higher dimension, this is a lot more complicated. What happens is that we get several different type of transformations. One type is divisorial contraction. This is similar to the case of surfaces where a curve is contracted to a point. Here, a divisor can be contracted to a point or to some other subvariety of maybe codimension 2, for example. And then there is another case of flips where we don't contract any divisor, but some curve are contracted. For example, on trifolds, it can be the case that one curve is contracted to a point. This is not analog to the case of surfaces. It's something completely new that appears only in dimension 3 and higher. But anyway, there is a sequence of well-defined transformations from going from X to hopefully to Y. So this is just a mimic in the case of surfaces, but a lot more complicated. Now, in order to run this program, we need to do a lot of local and also global geometry here. We need to prove many statements before we can actually run the program. And even up to now, we basically can run the program without, in most cases, we don't know whether the program will actually end with something or not. So potentially this could just go on for infinitely many steps and then not get anything in the end. But conjecturally, of course, that should not be the case. Okay, so then what I'm going to do now is to, from now on, we'll give you some of the steps, a bit more precise, the steps, at least what is required to carry out the steps of the minimal model program, and also just point out where Shokurov have made big contributions. So one of the, so there are lots of things that are needed here. One of them is called the base point free theorem. I will talk about it more precisely, and then contraction theorem. We need existence of flips, termination. We need to understand singularities as we go along from xi to xi plus 1 and so on. So this is quite a huge undertaking. Flips and singularities are new features which are just unavoidable. We can't just try to avoid them no matter what they appear. But in a way, that's not a bad thing, because it just makes things more interesting. It just says that the geometry is much more interesting, richer than the geometry in dimension 2. In fact, the MMP works in a much more general framework, and that's of pairs, where we take a variety x together with a boundary divisor b with coefficients between 0 and 1. So for example, b can just be a reduced a divisor. And then there are many good reasons why this we should work in this framework. One of the big reasons is that it makes induction proves much easier than otherwise. So a lot of things are done by induction in birational geometry, and this working with pairs makes it possible. Without pair, it's nearly just impossible. And for example, another reason is that if you are interested in studying open variety, non-compact varieties, and if you compactify it by adding a boundary divisor, then the geometry of the open variety corresponds in a way to the geometry of the compactified variety, but together with a boundary divisor. So there are quite good reasons to work in this more general framework. Although in most of this talk, I'll just focus on the case where b is equal to 0. Now, in some special situations, we can in fact run this MMP program on arbitrary divisors, not just on the canonical divisor. That is the case, for instance, on phonotype varieties. And toric varieties are phonotype varieties. So if you just pick any arbitrary divisor, you can run this program, and in the end, you will either get negative fibration or trivial fibration, or the divisor just becomes ample. So this is quite useful in many situations. Okay, so now let's look at what Shokurov has done. A very important ingredient of the MMP is existence of contractions. This is the analog of contracting -1 curves on surfaces. In higher dimension, the story is much more complicated. So what we do, let me just describe what we can do in general. Suppose that we start with X, a projective variety with good singularities, let's say KLT singularities, if you know what that means. And now the aim is, this big step of the classification is to make K as positive as possible. Here I say K nef. By definition, nef means that intersection with every curve is non-negative. So this is weaker than being ample, but it's just a numerical condition. Intersection with any curve inside X is non-negative. We want to make this K nef if possible, although that's not possible in every instance. What we can do is take an ample divisor A on X, and then we use this divisor A to measure how far this K is from being nef. To be more precise, we can define a number here, some kind of threshold T, where this is not a good notation. This should be T should be lambda or something. anyway, this is the smallest number such that k plus this number times a is nef. So if you take a very large multiple of a, k plus ta, if t is very large, this will automatically be ample because a itself is ample. So you just decrease the t up to a point where you cannot decrease anymore. There will be some place where k plus ta is not ample anymore, and then but it's still a nef. It intersects every curve now negatively, but it's not ample. So this threshold, let's just call it t. Now, if t is 0, that simply means that k is nef. Because if there is even one curve intersecting k negatively, then t cannot be 0. So this is just a simple statement. T is 0 means k is an f. And in that case, this x is basically equal to the y that we were looking for. Although to show that y satisfies the property of the conjecture, for example, that it admits Calabi-Yau vibration, is the statement of the abundance conjecture, which is a huge problem. So, but let's ignore that for the moment and focus on the case when t is positive. So that just means that k is negative on some curve at least. Now, what Shokurov proved here, he proved an amazing theorem in the mid-80s, which says that if you take a large multiple of k plus ta, then you will always get some section. And that is an extremely non-trivial statement. First of all, it's not even clear that the t is a rational number. And potentially it can be a real number, but the fact that it turns out, in a way, it's part of this whole statement and related statement that the t is in fact is a rational number. And then if you take a multiple, a large multiple of this divisor k plus ta, clearing all the denominators, then you will get for example, a Cartier divisor. And the statement is that some multiple has a section. And then from this statement, we can prove something, in fact, much stronger, which is that not only this multiple has sections, but if we take m large enough, in fact, the linear system given by the multiple by this m times k plus ta is base point free. It has no base points, and this will happen for a large m. This is a mixture of Shokurov result, this non-vanishing, together with ideas of Kawamata. So what we get from these two statements is that knowing that some multiple of k plus ta is base point free, that gives us a non-trivial morphism. It gives us a non-trivial contraction. Contraction here simply means it's a morphism with connected fibers. It's not necessarily birational. It can be fiber type of morphism, but so this is a very strong statement. We start with this x, we define this threshold, and then if t is not 0, then we have a non-trivial contraction. And in fact, every curve that is contracted by this morphism, by this contraction, these are precisely the curves intersecting this divisor k plus ta trivially. In particular, this tells you that this contraction x to z is a final contraction, meaning that minus k is ample over z. This just follows from the fact that a itself is ample and the fact that k plus ta intersect every curve trivially. So minus k automatically will become ample over z. So this process then gives you a non-trivial final contraction. In fact, conversely, every final contraction x to z arises as what we described. So if you start with any x to z where minus k is ample over z, then you can always cook up some ample divisor a. There will be some example in a few minutes where the contraction that is given by k plus ta is precisely this contraction. So this process is then just looking for identifies Fano contractions on X. Now, if X to Z is birational, then it's composed of flipping and divisorial contractions. So that just means that there might be a bunch of divisors being contracted. Maybe some other curves outside these divisors can be contracted. So in a way, this contraction is a little bit rough, so there are other cases where this is not birational, then we get Fano fibrations, for example, Mori fiber spaces. So for instance, if X is Fano, and if you take A to be minus K, then this process just tells you X to Z, X to a point is Fano, and that's it. It doesn't give you anything else. But if you take A to be some other ample divisor, then it can give you other non-trivial contractions. Now, if we combine this theory of Kawamata and Shokurov with Mori's theory of extremal rays, then we get a finer kind of process. We get just fine-tuning this process of finding these Fano contractions will give you exactly an algorithm which is precisely, in a way, the minimal model program. Although this program that I described is just telling you, giving you some kind of minimal model program. It actually doesn't give you, in a way, an arbitrary one. Because in the next step, it depends how we choose these divisors. But at least in the first step, it just can give you all these extremal rays and contractions. And of course, there were other people contributing to this story, like Benveni, Scholar, Reed, and so on. So I'm not going into those details. But let's look at the simplest examples where something like this happens. Suppose that we start, in a way, I'm going to do the reverse. Start with Z, a smooth variety, pick a smooth point, and suppose that Fx to Z is just the blow up of Z at the point, smooth point, little z. And then take A to be minus K plus the pullback of some sufficiently ample divisor H. So H lives on Z. Then I pull it back, I combine it, add it to minus K. If H is sufficiently ample, then what I get, A will be ample globally. And then in this case, the number T will be just 1. And K plus A is simply the pullback of this ample divisor. And the contraction that we get is nothing but X to Z. So in other words, blowups or inverse of blowups are one type of contraction that's possible to get in this process. So that's, in a way, that's the story of the minimal model, the program itself, and then this non-vanishing and base point freeness was extremely important. That was already understood in the mid-80s. But now another hugely important ingredient of the minimal model program is existence of flips. Now, why we need flips? We need them because sometimes these contractions that we get from X to Z, they don't contract divisors. For example, on threefold, they can just contract curves. And in that case, the Z becomes too singular. It's not the kind of singularity that we like in birational geometry. For example, you can't define intersection numbers anymore with the canonical bundle, which is not so good. So that's why we need a flip. And a flip here basically is just saying that you have this contraction X to Z. Now, one possibility is just go back to X and find some other contraction. But sometimes there is no choice but just to do something else here. And that's by, instead of going back to X, going to some other variety X plus over Z. In the threefold case, usually this means that X to Z, it contracts some curve where K is negative, and then on X plus, you have another curve contracted where K is positive. So at least you replace something negative with something positive. So something improves in this process. And this is called a flip. But why they should exist is a very difficult problem. Or it's not a problem anymore, but a very non-trivial statement. Now, this flip exists. This is equivalent to saying that this algebra given by all the multiples of the canonical bundle, we push them down as sheaves onto Z. So you get an algebra over the structure sheaf of Z. And if this algebra is finitely generated, then there is a flip. And in fact, if there is a flip, then this algebra is finitely generated, and its proj will give you precisely this X plus. So flip here is then not only a geometric statement, but also a very algebraic statement. Now, a great result of Mori in the late 80s says that flips always exist in dimension 3, at least for threefold singularities. But to work out this statement in more general, in deeper singularities, and also for in the log version for where you have also a boundary divisor, is another amazing achievement of Shokurov in the early 90s, when he proved that log flips exist in dimension 3, basically in the most general possible case. So that was very important also to prove other statements that usually involve pairs, not just one single variety. And in fact, he proved this theorem in, I think, one of his best papers, which is called threefold log flips. In this paper, he also introduced many other very interesting notions and techniques, for example, complements and so on, which played a central role in solving other problems in higher dimension. Now, again, in the mid-80s, Shokurov, in fact, proved termination of flips in dimension 3 in the terminal singularity case. So combining that with this contraction theorems and Mori's theorem on flips, then we could run minimal model program starting with any smooth threefold, and it would terminate with some model, which is exactly that Y in the conjecture that I mentioned. But the more general version of the termination was later proved by Kawamata. So combining it with Shokurov log flips statement theorem, then now we could run the minimal model program in the most general possible sense on pairs in dimension 3. So that was up to the early 90s. And just about around that time also, in fact, you could say that the log MMP in dimension 3 was basically completed. I mean, by that time, I'm getting from X or XB to Y. That's because we already had Conan contraction, we had flips, we had termination, but also log abundance meaning that when you arrive at Y, there should be some vibration. That was also solved by work of Miyaoka, Kawamata, Kiel, Masuki, McKernan, and of course there were also other contributions of Reed, Kohler, and many other people, which I better not go into the detail. So up to the early 90s, about maybe 92, there were then this minimal model program was basically very well understood in dimension 3. So that just took something like, I don't know, 15, 20 years. But then there was a period of drought. Basically from early 90s to early 2000s, there weren't really that many results. There were, of course, interesting results, but comparing it to the 80s, I think that you could say this was a period of drought. Not very fundamental things proved in this period, until in the early 2000s, there was another amazing paper of Shokurov, again on flips, this one called Prelimiting Flips. In this paper, he proved that log flips exist in dimension 4. So just getting from dimension 3 to 4 was an amazing, a huge step. So that took something like a decade for him to work out. And then a couple of years afterwards, he also showed that, in fact, you can prove existence of minimal models in dimension 4. That doesn't include the abundance part, just the fact that if you start with xb, you can always get some y. That was established in dimension 4. So it's obvious that how much he has, how fundamental role he has played in shaping this field in dimension 3, but also in dimension 4. But in fact, this paper, Prelimiting Flips, it also contains a lot of ideas of what to do in higher dimension, not only dimension 4. In dimension 4, there was an unconditional theorem. It in fact also gave a very simple and nice proof of existence of flips in dimension 3, but it also told you at least what to do in higher dimension. Now, when this paper appeared, I was a first-year PhD student. I just actually started doing PhD in algebraic geometry, and I tried to read this paper of Shokurov, and not so surprisingly, I had a very difficult time to try to understand some of the details of this paper. And then there was a whole program on this paper at the Newton Institute in Cambridge in 2002. And toward the end of the program, finally Shokurov showed up, and I met him, and I found him to be a very kind person, and he also agreed basically to be my second advisor. I already had an advisor, Ivan Fesenko, in Nottingham, but then since I was working in birational geometry, obviously it made sense to also work with someone in the field. And this photo is taken on the campus at Johns Hopkins University. I think it's about around 2003. But then a few years after this prelimiting flip paper of Shokurov, then Heiken and McKinnon proved another great result. They showed that in fact log flips exist in every dimension, assuming that you already know the minimum model program in one dimension less. So for example, you could just get, because dimension 3 MMP was already known, then you get another proof of log flips in dimension 4. And then it didn't take long before these requirements were also worked out. So then just 1 year later, in a paper of myself, Kashini, Heiken, and McKinnon, then we showed that these flips exist unconditionally in every dimension. But I would just want to stress out that Shokurov's ideas and techniques and arguments played a key role in all these theorems, in all these statements. Of course, there were also very new ideas in these results, but we should just not forget about Shokurov's contributions here. Okay, I think that's enough for flips and minimal models and so on. Let me say a few words about final varieties and complements. Now, I actually don't even know what time I started. Can someone remind me, please?
About like I would say 55 minutes ago.
55 minutes? 55 minutes? Okay, so maybe I will go a bit. Although I was told that this is a Russian style seminar, so I can go.
Look, half an hour for sure. And if you want more, take more. I mean, look.
Okay, so I will try to make it not too long. I think people are not used to. Russians are used to, but maybe not all the participants. Okay, let me say a few things about final varieties and complements, where Shokurov also played a key role. In fact, one of the very earliest results of Shokurov in birational geometry is about final varieties. What he proved was that, so this goes back to like late 70s, if you take any smooth final threefold, then there is always a smooth K3 surface in the anti-canonical system of this final variety. More generally, if minus K happen to be a multiple of some Cartier divisor, then in fact, there is always a smooth surface in the linear system given by this Cartier divisor, let's say L. And this result was, in fact, amazing in several ways. First of all, it it provided some of the technical details for classification of final threefold. This is exactly the things that Iskovsky needed to do classification of final threefolds. But looking at this paper, you can in fact see already elements of the base point free theorem already appearing in this paper, where you have divisors, you restrict to some other divisors, you use cohomology to leave sections, and so on. So it's quite interesting in a way. So this result complemented work of Iskovsky, Mori, and Mukai on classification of final threefolds. However, it played another really important role. This is, in a way, the origin of Shokurov's theory of complements. Complements, in general, if you are on a final variety X in any dimension, with can have deep singularities, an n complement is simply an element of the linear system given by minus nk, so that if you divide this divisor by n, you will get a pair, and we want this pair to have low canonical singularities. So to have an n complement is basically two statements. One is that there is a non-vanishing where minus nk has some section. And another thing is that some element in this anti-canonical system, anti-pluricanonical system, has good singularities.
I'm sorry.
Yeah.
This n, does it have something to do with the dimension?
Yeah, I will come to that in a couple of minutes. Yes. Now you can define this complement also. Yeah, I will answer your question in maybe 2-3 minutes.
And is X smooth now or not?
No, I mean, I'm taking KLT singularities, but even for low canonical, of course, it makes sense. But I will mostly stay with the KLT singularity. So this is not smooth anymore. And
okay.
In general, you have to take some n's. In the smooth threefold case, n was just 1, basically. But when you go to higher dimension, or when you go to deeper singularities, minus k may not have any sections. So you are forced to go to some higher multiple. Now, the interesting thing about complements is that you can also define them in the relative setting when you have a final contraction. In fact, if x to z is just the identity morphism, we can regard that as some kind of final contraction. And even in that case, the existence of complement makes sense, and it tells something about singularities. So this is a quite interesting theory. And Shokurov used this complement theory in his proof of existence of threefold flips. Because when you have a flipping contraction, this is a final, relative final contraction, so it makes sense to talk about complements. And he showed that you have complements, and he used them to derive existence of flips. But he also used them later in the classification of threefold singularities. This theory then was further developed by Shokurov himself for surfaces, and also in higher dimension by Shokurov and Prokhorov. And Shokurov conjectured, in fact, that bounded complements exist. Let me just state it as a theorem, which was proved just a few years ago. They say that if you take any final variety with KLT singularities, then an n complement always exists for some fixed n, depending only on the dimension and not on the variety. This is a really amazing statement, because such x form a huge family. They are not like bounded or anything. The fact that there is some n depending just on the dimension, not even on the singularities, is a really amazing conjecture of Shokurov, and this has played a big role in other statements. In fact, this statement is central to proving boundedness of final varieties, this conjecture of Borisov and Alexiev. And then it's important, for example, to, based on this conjecture of Alexiev-Borisov, to derive Jordan property of Kremonov groups. This was worked out by Prokhorov and Shramov. It plays a central role in studying singularities in works of myself, Han, Lu, Shokurov, Moraga, and so on. it is important to study local labial vibrations in general. This, again, in work of myself, Di Cervo, and Svaldi. And also it plays a central role in construction of moduli spaces for k-stable Fano varieties, for example. And I think it's important we'll just go beyond these things. So you can see the role of Shokurov in all these stories. Now, I prepared some conjectures, but I think I will go a bit fast through these things, just to point out that Shokurov not only proved many amazing results, but he also proposed many amazing conjectures. And so far, he has a 100% success rate in the sense that none of them turned out to be incorrect. I think that also is an amazing thing. Now, one of these conjectures he made was about behavior of singularities. This is called ACC for low canonical thresholds. In its simplest form, this says that if you have a variety X with low canonical singularities, and if you have an integral divisor M, it has to be Q Cartier, some multiple should be Cartier, then we can define the low canonical threshold of M with respect to this variety to be the supremum of the T, the number T, such that XTM is low canonical. So it's the largest multiple where you are still inside the category of low canonical singularities. So each X and M will give you one number, but the conjecture says that in fact the set of all such possible T in fixed dimension satisfies the ascending chain condition, in the sense that if you look at this set, you cannot find any strictly increasing sequence of these thresholds. This is a really amazing statement. It was proved some years ago by Haken, McKenna, and Zhu. And then there is another much tougher conjecture about singularities. This is about ACC for minimal log discrepancies. It says that if you are given a variety X, you can define an invariant of singularities. It's called minimal log discrepancy. In a way, this is like the worst possible singularity on X. It's just a number. It will give you a number. Then the conjecture says that the set of all such MLDs in fixed dimension again satisfy the ascending chain condition. This is a hugely important, but also very tough conjecture. It's still open even in dimension 3. Now another conjecture of Shokurov is about boundedness of complements. This is a more general form of what I discussed before. It says that if you have a Fano contraction, let's say Fano vibration, where the total space has singularities bounded by some number epsilon, just means MLD should be more than or equal to epsilon, epsilon is positive, then there always exists a KLT, and here is the key. KLT, not low canonical. There is always a KLT n complement for minus k relatively over z for n depending only on the dimension and on this number epsilon. Now, if you replace low canonical, if you replace KLT by low canonical, then this was already proved that I mentioned in my work. But assuming KLT makes this thing a hugely more complicated conjecture, this is definitely probably the toughest conjecture that I have talked about so far. And this is, again, this is open already in dimension 3. It, in a way, expectation is that this should imply even the previous conjecture and what comes even after. So the final conjecture is about boundedness of singularities in Fano-type vibrations. This is more technical, so there isn't much point into getting into too much technicalities, but it says that if you start with a pair XB where the singularities, again, you can define some kind of MLD, this is more than or equal to epsilon, epsilon being positive. And if you are given a local Abiyao vibration, which is a Fano type, meaning, for example, that the general fibers are Fano, then there is an induced log structure on the base. You can define BZ in some way, given by the so-called canonical bundle formula. And the conjecture says that The singularity on the base will also be bounded by some number delta, where the delta depends only on epsilon and the dimension. Now, it's not difficult at all to derive this conjecture from the previous conjecture on boundaries of complements. Again, this is still open even in dimension 3. Okay, I think I will stop here. I probably said enough about contributions of Slava Shokurov to mathematics. I think what I already said, without even mentioning his other works, makes him one of the really greatest mathematicians in birational geometry, in algebraic geometry in general. Okay, I stop here.
Thank you very much. Let's thank the speaker. Questions? Comments? Apparently so intimidating, like the whole corpus of Shokurov's work. You don't even know what to. Well, a stupid question. What about termination of flips? It's still open, isn't it?
Yes, termination of flips is still open. Even in dimension 4, it's open in full generality, although it's known in many cases. But in higher dimension, only some special cases are known. Otherwise, it's still wide open.
Okay, but somehow it turned out we don't need it for the minimal model, right?
I mean, we don't need it in full generality, but we still need some. If you start with a variety and you run with minimal model program, if you know at least some choice of the program terminates, that's enough for most applications. But even that we don't know. We know only in the case of general type.
All right.
If X is not of general type, then and if X is not like uni rule, then we don't know whether this program terminates.
Okay.
Okay, may I comment about needed or not? There exists paper of Hahn and Haken about this connectedness. Do you hear me?
Yeah, we can hear you.
They use full format termination. It's impossible to prove without.
Yes, yeah, of course, this is important. Full termination is important for some applications. But I think for many applications, we only need a special kind of termination. But for example, yeah, another instance is that this generalized pair, which is more general than what I discussed. One termination of this, then full termination is important.
Format termination. It allows some cases. Some problem with sound.
We can hear you.
No problem.
Okay, now I can hear sometimes your comment. Okay.
Kosher, you estimate, will all of Slava's conjectures be proved eventually, like within 10 years?
Yeah. I expect that maybe take a few years. I think this complement conjecture is maybe the most important and the most difficult among them, because it likely to imply everything else that I mentioned.
Okay. But will there another period of drought, or is it actually moving on?
Well, hopefully not drought. I mean, there are other problems. Of course, these are important conjectures, but there are other important conjectures in the field or related to birational geometry. So there is still plenty of things to do.
Okay. I mean, I'm just an outsider, but that was my impression, that there was like 10 years of nothing, but then it's going on strongly for the last 15 years or so. Well, anyway.
Kosher, may I ask you, what is the most important conjecture in birational geometry from your point of view?
I think I could pick two. This complement conjecture and abundance. These two are the top two. In a way, they don't seem to be related, so you have to separate them.
I see.
You said that termination of flips was proved in some partial cases. Can you tell more about this, about partial termination of flips?
Yes, so there is a kind of termination called termination with scaling, which is actually more or less what I described in the program, that we start with X, we take some ample divisor, we take a threshold, and so on. If you continue this step by step, but staying with the same divisor, A, this gives you some kind of minimal model program, which is called minimal model program with scaling. Now, if X is of general type, we know this terminates. This is true DCHM. And also, if X is, for example, is uni-ruled, let's say X is smooth and uni-ruled, then again, this program terminates. So it terminates in many interesting situations, but in full generality, we still don't know whether it terminates or not.
So even with scaling, you don't know?
In dimension 4, we know, but not in higher dimension.
There is one interesting result of Birkar in this direction. If for effective pairs, then log canonical threshold gives complete termination. You can ask.
Yes, I mean, that's assuming full termination in lower dimension. Then when you go to higher, one dimension higher, and if your quadratic dimension is non-negative, then again, full termination holds.
And do you know something about termination of flops on Calabi-Yau manifolds?
Yes, I mean, again, on Calabi-Yau manifold, you take a divisor, so you have a sequence of flips. I mean, I don't know any general statement that this should terminate. If the divisor is big, then it will terminate. At least it's scaling. But otherwise,
if the divisor is big, then a sequence of D flops will terminate.
Yes, that's just follows what I said. Otherwise, in dimension, I don't know, 6, then we don't know whether this, for arbitrary divisor D, whether this terminates or not.
So it's known for log pairs of general type.
Yes, in that case, it's known, but otherwise it's still.
So log flips for log pairs of general type. Okay. Thank you.
All right. So maybe if there are no more questions, let's thank Kosher again.
Can I ask a question?
Go
You had this conjecture that you get these vibrations from the fibers. The general fiber K is trivial or positive or negative. But I mean, in principle, you could have a fiber which is a Calabi-Yau variety divided by a finite group. How can you, I mean, this is, I mean, in low dimension, it is true that if you take abelian varieties and you take hyperelliptic manifolds, then you find some vibration in toric. But what would be the strategy to think that this is true in higher dimension, that really you have a fibering where the K is trivial and not torsion on the fiber?
That's the difficulty to prove, whether there is a Calabi-Yau vibration or not. That's the main thing to prove. If we already know that there is a Calabi-Yau vibration, then we can inductively we can prove what we want. This is not a difficult case. The difficulty is when you arrive at suppose, let's say Kodaira dimension is 0. Then we conjecture Y should be just a Calabi-Yau variety, but we can't prove that. That's exactly the statement of abundance. If you already have some vibration, but usually you can do induction to prove anything.
More questions? Comments?
Will we have a drink?
Yeah, let's thank Kosher again for his great talk, great overview of great work, great work.